You know that quiet moment right after you hit compile? It can almost feel like magic, right? All our complex human ideas somehow get transformed into something a machine can actually understand. But it isn't magic. It's really just a beautifully organized conversation. So today, we're going to peek behind the curtain and listen in on one of the most important yet mostly unheard languages in that whole conversation. So let's really think about this for a second. We write code in these languages that are built for us. They're full of complex logic and symbols that we get. But a computer's processor, it speaks a much simpler, more direct language. So how do we bridge that massive gap? How does our creative, kind of abstract code actually talk to the super literal, logical computer? Take a line of code just like this one. To you and me, this is a piece of cake. We immediately see the order of operations. You do the multiplication first, then the addition. Simple. But for a computer, this single line is like a complex sentence that it needs to diagram before it can figure out the steps. It doesn't see a to-do list. It sees a puzzle of relationships. So, the very first thing a compiler does is create a plan. And this isn't about running commands just yet. Not at all. It's about deeply understanding the structure of what we've written. You can think of it like an architect drawing up a really detailed blueprint before anyone even thinks about laying a single brick. And this right here, this is that blueprint. It's called an abstract syntax tree. Now, what's so cool about this is how it visually maps out our code's logic. You can see how the tree shows that the y times z multiplication has to happen first, right? Because it's on a lower branch. And then its result becomes part of the addition with x. It perfectly captures that hierarchy, those rules we all learned back in math class. So here's the key thing to remember. While this tree is absolutely fantastic for understanding the structure, it's not a linear set of instructions. A processor doesn't climb trees. It just executes a straightforward, step-by-step list. This beautiful, abstract blueprint, well, it needs to be flattened into a simple, actionable to-do list. And this is where our unsung hero finally comes in. To solve this very problem, the compiler uses what's called an intermediate language. It acts like a universal translator, breaking down that complex blueprint into something much closer to what the machine can finally understand. And this language is called 3-address code. And this slide just illustrates that translation perfectly. On the left, we've got our complex, branching syntax tree, and on the right, you see it transformed. The expression is broken down into these simple, separate steps. The compiler even creates a temporary variable, t, to hold a result in the middle of the calculation. All of a sudden, our branching tree has become a flat, sequential list. It's this amazing process of turning complexity into clarity. So what exactly is 3-address code anyway? Well, it's basically a sequence of really simple instructions, and each instruction has at most one operator. So no more y times z plus x all in one big go. The general form is beautifully simple. You have a result and it's assigned the value of two things, your operands, combined by a single operation. That's it. Okay, let's make this even clearer. The name 3-address comes from the fact that each little instruction can be thought of as referencing 3 locations or addresses in memory. So for an instruction like t1 equals y times z, you have the address for the result, which is t1, the address for the first thing you're working with, y, and the address for the second thing, z. 1, 2, 3. It's really as simple as that. Now, all this simplicity might have you wondering, why bother? Why go through this whole extra step? Why not just go directly from that syntax tree straight to machine code? Well, it turns out that this simplicity has a hidden power, and it's all about making our software smarter, faster, and way more efficient. And you know, the source text really hits the nail on the head here. This intermediate form is desirable for optimization because it allows 3-address code to be rearranged easily. Because each instruction is its own little self-contained simple piece of logic, the compiler can now look at this whole list and find clever ways to improve it before making the final code. So what's the big payoff here? Well, it means the compiler can easily spot and get rid of redundant calculations. It can safely move instructions around to make better use of the processor's time and energy. Basically, by breaking our big ideas into these tiny, manageable pieces, the compiler gets a much clearer view of how to build the fastest, most efficient program it possibly can from our code. Here's a good way to think about it. It's like organizing your kitchen before you cook. You wouldn't try to chop vegetables, boil water, and mix sauce all at the same time just by reading one big paragraph in a recipe. No way. You'd break it down into a list of simple, single-action steps. First, get out the ingredients. Second, chop the onions. Third, boil the water. That intermediate to-do list, that's your 3-address code. It just makes the final process of cooking, or in this case, generating machine code, so much more organized and efficient. And that really brings us to the heart of this whole thing. This process, three-address code, it's not just some technical detail. It's the quiet, absolutely essential bridge that connects two vastly different worlds. I mean, think about it. On one side, you have our human way of thinking, which is creative, it's abstract, it's complex. And on the other side, you have the machine's world. It's rigid, it's literal, and it needs a simple step-by-step list. Three-address code is that unseen translator that makes this whole conversation possible. It's the hidden foundation that lets every single piece of software we use run as well as it does. So, the real takeaway here isn't about memorizing compiler theory. It's about appreciating the elegance you can find in simplicity. A little reminder that often the most powerful solutions come from breaking down complexity into clear, manageable steps. The next time you hit compile and watch your idea come to life, just take a moment. Appreciate that silent, methodical process, the hidden, organized language that patiently turns the complexity of our thoughts into the clarity a computer needs to make it all happen.